me call it n tensor, okay, like this. And this is in the space H, in this space. So essentially, if I have a linear map from any vector space to a pre-Hilbert space, I simply use this pullback, so-called pullback map, to define a scalar product on the original space. So notice that if the vector V is in the kernel, this is an homomorphism, okay? So it may have a non-trivial kernel. However, if I have a non-trivial kernel, this means that T is T of V1, Vn will be 0 even if Vn, V1 are not 0, okay? Then this means that the same must be that this vector will be 0. So in particular, we'll have 0 norm. And so when I use this scalar product on this space, the kernel of this map is in the 0 norm vector. Clear? Automatically. And therefore, the kernel is in the 0 norm vectors, so I can define modulo 0 norm vectors. I can define the inverse. Essentially, the inverse is defined on the quotient space. It's defined modulo element of 0 norm. So now, when I have transported this, now what happens? You see, it is an interesting calculation that we can do. Remember that this by definition T of V is this, so I can write this. Now, let me write this in this way. This is Vn. Here I have Vn minus 1. And then I have V1 and V. So, I can write this part of the vector, and of course I have the scalar. Now, the left-hand side remains the same. I don't rewrite to gain some time. This will be A daga Vn times T of what? Of this A daga Vn minus 1 A daga V1 applied to V. Okay? So, using what I said before, that the inverse of T is well defined, modulo a vector of 0 norm, which are not important because there is a scalar product, and vectors of 0 norm are orthogonal to everything.
So, like how is
T is this map.
Yeah, then
Is the map that T is clear what is T or not? Is clear or not?
T is from V tensor.
T is this map.
Yeah, but N is valid.
T is the map
There you have
which to the tensor product Vn tensor V the tensor V1 associates by definition, for every n. I don't put Tn, but
Yeah. But there you have a Vn minus 1 plus that vector belongs in Hn minus 1.
Yeah,
that is why I don't put T. This is for every n, because I consider this. I mean, I should, if I want to, in fact, in the notes and in the paper is written so, but I want to gain time, so I should have written this Tn.
that's okay.
Then I define a certain operator T, which by definition is the orthogonal sum of all Tn, and of course by definition.
What it means is that there you have T of Vn minus 1 tensor V1, etc. On the right side.
You have
T of the
Yes. Very good. Sorry. You're very correct. You're right. This is Vn minus 1 tensor and no phi. Thank you, see. This is correct. V1 and that's all. Okay? And now, using the fact that we have the inverse, so, using the fact that, so let me say, this vector here, okay. This vector here is also of the form T of something. Okay? Now, using the fact that we have a well-defined inverse, I can simply multiply and divide here by T minus 1. Okay? So, I have T of something and T here. So, this means that I have UN tensor U1, and then it remains T minus 1 a daga n, a daga Vn T acting on V n minus 1 tensor. Okay, because I put this and here I put parentheses here. Now, and this is closed. So, what does it mean? But I know from the definition of my scalar product, you see, I know for the definition of my scalar product, which is this one, I know that this is also equal to we call the universal tensor homomorphism. Under the universal tensor homomorphism, the creator in the pre-Hilbert space will go into an operator that we will call L star of V, which has the property that to a vector V, an element for each n, as always, in any tensor space. We can put also n. Here we have n minus 1, but I can put also n because n is arbitrary. It will associate V tensor so is well known in the literature, is called the free creator. In free probability, this is the creation operator. You see that simply it comes from the natural fact that any multilinear, remember we are taking usual tensor product for the moment. Okay? So we have this operator. So we have what we have proven with this discussion. So we have shifted for each n the scalar product on here. And then we have also defined, we have also shown that with this T homomorphism, the tensor homomorphism, then the creator is mapped into a well-defined and simple operator. So we obtain, what we obtain? We obtain a structure which is my original interacting Fock space. You see, since T is defined as a sum of Tn, by construction T is gradation preserving. So all isomorphisms are gradation preserving. And this shows that, obviously by definition, this will bring is of degree +1. So it means that is a interacting Fock space with gradation Hn and creator map A daga. This is, we started from an arbitrary interacting Fock space, and we have proved that it is canonically isomorphic to an interacting Fock space which is given by the tensor product of the original space V, real or complex, it doesn't matter, with the scalar product that we have defined. Pay attention, this scalar product, n power tensor. So this is V, and with the free creator map. This is what we have. This is called the tensor representation of interacting Fock space. So any interacting Fock space has a tensor representation. But pay attention, this product, this scalar product here, gives a certain scalar product on the tensor product. But even if I started with a pre-inverse space V, this scalar product has nothing to do with the scalar product on V. Okay? So that is why the correct category is vector space, because the scalar product is induced. Okay?
And unique subjectivity of T which will follow from that condition is it AV plus Hn is
what?
Like here for this identification of the abstract interacting Fock space as V tensor, like the tensor algebra of V, you need this operator T to be surjective, like the T that.
But it's surjective by definition.
Yeah, that's what I'm saying.
We have said that this system of linear is even more than surjective. It's surjective it's surjective in the vector space. So that linear base is a set of linear generator go into a linear generator. We are all at the algebraic level, no topology for the moment.
So for that you need this condition, right? I mean this AV plus Hn is equal to Hn plus 1 for the abstract Hilbert, for the abstract.
For that I need this condition. For the millimality condition. Okay? So we have proved this. Now, this so this is a tensor representation. Among the tensor representation, there are many interacting Fock spaces, but a very famous example is the following. Take the interacting Fock space given by the powers. Now we start from a pre-Hilbert space. Now we need take V is a pre-Hilbert space with the scalar product, pre-scalar product of V. Then we can form the interacting Fock space with the creator map, with the interacting Fock space with nth scalar product, given, that is why I wanted to keep this symbol, and by the free creator map, to distinguish from free creator. Free creator is the map applied to a vector V, which gives an operator. Okay? So, what is this scalar product? The scalar product is un tensor u1 gn tensor v1. By definition, this scalar product denoted star n is the product of the individual scalar product. Okay. Now, if I have this, now let me consider, because it will be crucial for us, we will prove that when...
maybe you should tell what is L star.
What is? L star is the free creator, because the free creator is algebraic. You see, this can be terribly complicated, but this is universal. This is algebraic. I simply take V1, Vn, and I multiply on the left. I tensor multiply on the left. So this works for every interacting function, because the interaction is in the scalar product. That is where we keep our interaction. Okay? Interaction means that you have very complicated things. This is the simplest choice. This is the famous choice. This corresponds now. We are not yet to quantum mechanics, because this is not, in the quantum mechanics we have not the tensor product. What we have in boson, we have symmetric tensor product. Where does it come from? Definition. An interacting Fock space. Remember that this has to give a family of scalar products and a creation map. It's called symmetric. If the family of creators is a commutative. There is if I take the product in this family, the family of creators. This is very important. From where does it come, this definition? Again, the orthogonal, we will do in the next lecture, we will show that when we go from dimension 1 to dimension n, the polynomial algebra is isomorphic not to the tensor algebra, but to the symmetric tensor algebra. This is a very famous and old result of classical linear algebra. That is, the algebra of when we go from one variable to two variables, then it must be symmetric. So this object canonically arises in the theory of orthogonal polynomial. Okay? How this theorem generalizes? Well, this theorem generalizes in a simple way. That we have only to be this is also well known from old linear algebra, that universality, the universal tensor map, like this T, has the property that when I restrict to the, let me say so, if I have T, if I define now my map, let's call it T hat, it will go from, it will map Vn. I use hat to denote the symmetrized tensor product. So this is V1. A symmetrized tensor product means, by definition, that you apply the symmetrizator, which is a projection, where sigma belongs to all permutations of the indices. Okay, so this is the definition of the symmetric tensor product. Okay, you easily see that this is a projection at a vector space level, linear space level, and so I will map this vector into a diagram, the same as before, exactly the same. The range is exactly the same, but now the creator commute, so this expression gives you not a n-linear form, but a symmetric n-linear form. And the universal property is true also for symmetric maps. So this goes A, V, N. Okay? So we can repeat essentially with no big difference the discussion that we did. I have written the details in the lectures, but here the time is terribly rushing. So I will just give you the main idea. Okay? So we have this, and